Hi guys, it's your science teacher here, back with another video. This time I'm going to go through the whole of my predictions for chemistry paper 1 exam for 2022. Now, I haven't just come up with my prediction from my own knowledge. I have used AQA's website on what topics they've said that they are going to include on this year's papers, and what topics they said that they're not going to include. So without further ado, let's get started with today's video. Let's firstly look at where I got my information for about what to put on this video. I went to the AQA website and looked at the things that they said are key to this paper, and also things that won't be assessed in this paper that I've not included in the video. Also, what's key is these required practicals, and that's where I'm going to start off actually. I'm going to start looking at these 3 required practicals, and the 3 required practicals on this paper are actually the same for both higher and foundation, and same with most of the bullet points as well. So there is a lot of overlap between the higher and foundation topics for chemistry. Let's start by looking at the first required practical, which is the preparation of a pure dry salt. And in any reaction, you need to carry the reaction out first, and we usually do that in a conical flask. Now, some of these reactions need a bit of activation energy to get started, so sometimes you will need to heat up your reaction mixture. But usually in the preparation of pure dry salt, we always add excess of whatever base we are adding. Depending on what salt you are making will depend on the acid you use and the base you use for your reaction. And we're going to look at later in the video at naming some salts from different acids and bases. So because we've added excess base, what we actually have to do next in the preparation of our salt is filter out the excess base. And the reason why we are adding this excess base is because of the fact we want all of our acid to have reacted. After we've filtered, we evaporate. And the evaporation is what starts off our crystallization. We'll get rid of some of the water. Usually we evaporate till half the liquid has gone. And what we do next is we leave on the windowsill to crystallize. And this stage is vital if you want to create big salts. The longer you will leave it to crystallize on your windowsill, and the less liquid you will evaporate. Also, when you evaporate, sometimes you can get a bit of product loss. So this is another reason that we leave it on the windowsill to crystallize. The next required practical we're going to look at is by changing different variables, measuring the temperature change. Now, this could come up and you could have a few different independent variables. You could have the amount of metal that you add to a mixture and measuring the temperature change, that be your independent variable. Or you could have the concentration of acid. So they could do this a few different ways, but there's some rules that will be the same for all of them. So, for example, if the independent variable is the amount of metal that you're adding to your solution or acid, then what you need to do is make sure that the concentration of your acid will be a control variable. And vice versa, if the concentration is what you're changing as your independent variable, then the amount of metal that you add would be your control variable. But the dependent variable is always going to be the same for this practical. You're going to be measuring the temperature change. Now, to get the temperature change, what you need to do is you need to do the new value of temperature minus your initial value of temperature. In addition, if they gave you this practical setup, they might ask you what you could do in order to make your results more accurate. Well, here we've got a thermometer measuring our temperature change, and what we could do to make that more accurate is we could use a digital thermometer, or we could use a data logger. which would more accurately measure temperature change. As well as this, what we could also do is add a lid onto our practical setup. This will reduce heat losses, so you're going to get a better value for your temperature. You could also add insulating material around the outside. That would result in you getting more accurate results as well. And a couple of things just to remember is if the temperature of your solution goes up, then it's exothermic. And if the temperature of your solution is going down, then that is an endothermic reaction. The next practical is titrations, and this is probably the hardest one to get your head around. And let's first start by looking at the different pieces of apparatus that I have in a titration. And firstly, I have my burette here, which is how I add my known concentration of solution. So in this example here, I know the concentration of hydroiodic acid, so that would be in my burette. And I will use a pipette to add my unknown concentration of solution, which in this case would be calcium hydroxide, into a conical flask. The reason why I use a burette is because I can add this solution dropwise. And once I have my unknown concentration in my conical flask, then I add an indicator to it. In this example, I have an acidic solution in my burette. So what I want to happen is I want to add an indicator which will change colour when it starts to become acidic. And there's a couple of indicators you can use. You can use phenolphthalein, which is pink in alkaline and it goes colourless when it becomes acidic. Or you could use methyl orange, which is yellow in alkaline and it goes red when it becomes acidic. Now, what is really important with titrations as well is to take repeat readings. Now, the first titration that you run will just to be getting a ballpark number so that you know that 2 centimeters cubed before that value, you should start adding dropwise. And then when you get a few concordant results, that means that you can then take an average from them results. What I mean by concordant results is results that are close together, maybe in between 0.1 centimeters cubed of one another. Okay, now let's have a look at how I could actually go about doing this calculation in order to calculate my concentration of calcium hydroxide when I have this known concentration of hydroiodic acid. And I know the volume of both of them, and I can start by calculating the number of moles of hydroiodic acid first. And the way I actually do these calculations is I draw a line down the middle. I write myself acid, and I also write alkali, and I write NCV for both of them. The N stands for the number of moles, C for concentration, and V for volume. And then I will just write down what I know for all of them. Now, the first thing to do is turn my volumes into decimeters cubed, because that is what my concentration's been measured in. It's moles per decimeters cubed. That's what this big M stands for. And that for my acid would be 0.0211, and that for my alkali would be 0.025 dm cubed. Now what I can do is write in my concentration. I know that for my hydroiodic acid, that's 0.75 m. Now to calculate my number of moles, I just do my concentration times by my volume. And you can do this with me if it helps. So 0.75 times by 0.0211 is 0.015825. Now I'm writing in all my sig figs here because of the fact that This isn't the number that's going to be important to my calculation. It's going to be the concentration down here that I'm working out. So I'm going to carry this number through in other calculations. To get the most accurate value, I just need to include all my sig figs. Because I know my number of moles of acid, I can now easily work out my number of moles of base, because I've got a 2 here. It's in a 2 to 1 to 2 to 1 ratio. So if I have 2 moles of acid, I have 1 mole of calcium hydroxide. So if I divide this number by 2, I'll get the correct number of moles of my base. And that calculation gives me 7.9125 times 10 to the minus 3 moles. Now finally, what I can do is work out my concentration by doing my number of moles divided by my volume. So this 7.9125 times 10 to the minus 3 divided by 0.025. And that gives me an answer of 0.3165, capital M for my units. Now, depending on how many sig figs it wants in the question, it depends on what you'd leave your answer as. But here in the question, there is 3 sig figs for the volume, so I'm going to actually leave my answer 3 significant figures, so 0.317 moles. That's my answer. Underline it, circle my units, perfect. Starting off in chemistry, I think it's always dead important to know the fundamentals before getting into some of the maybe more tricky stuff. And here you might be able to see which atom I've drawn already just because you know some of the rules. You can see that it has 3 electrons in its outer shell, and that means the atom I have drawn is lithium. And you can see that my purple subatomic particle must be the proton because there is also 3 of them, and we know the number of protons from the atomic number, which is my bottom number. So my bottom number, which is the atomic number, tells me how many protons and how many electrons that you have inside your atom. As well as this, lithium has 4 neutrons. The way you can tell there's 4 neutrons is because you do the atomic mass minus the atomic number. 7 minus 3 equals 4, and there is 4 neutrons inside the nucleus of my atom. I use the term nucleus, and that just means the central part of my atom. Then around the outside, I have my electron shells. Now, lithium is in period 2 of my periodic table, meaning it's the second row down. So it has 2 electron shells and it has 3 electrons. Now, if I was to write out the electron configuration of lithium, it would just be 2 and 1. And the reason why there is only 2 electrons in my first shell is because all atoms follow something called a 2-8-8 rule. And this means that 2 electrons can go in my first shell, 8 can go in my second shell, and 8 can go in my third shell. Now you may also notice I've represented my electrons with crosses. Electrons are very small, that's why I haven't represented them as spheres like this. Now, other things to know about your subatomic particles is your protons have a charge of +1, your neutrons are neutrally charged, and your electrons are negatively charged. Now, because of the fact that in an atom, the atomic number, which is 3 here, tells you the number of protons and electrons. This means overall atoms are always neutrally charged because the number of protons and electrons is the same. Now that we've covered some of the fundamentals, we can go on to looking at a few things that might be a little bit more tricky and a bit more interesting. And the first one is looking at how the periodic table has been developed over time. And the first person to realize there was a bit of a trend going on in the elements was John Newland. And what he noticed was about every 8 elements, patterns started to repeat themselves. And some of the properties were the same, so he put them into columns, the elements. And although he was quite successful in his first version of the periodic table, it wasn't perfect, and quite a few scientists were skeptical about his law of octaves, and there is a few reasons for that. The first being that he's put copper in the same group as the alkali metals. Now, if you know copper, you'll know that copper is incredibly unreactive, whereas lithium, sodium, and potassium are known as alkali metals, and they're incredibly reactive. So scientists were a bit confused by the fact that he'd done this. Also, he's put two elements in the same box, and this was a big no-no for a lot of scientists. And as well as this, he has also mixed up some metals and non-metals and put them in the same group as one another. For example, here I've got hydrogen, fluorine, and chlorine, which are non-metals, and in the same group he's put cobalt and nickel, and these are metals obviously, and they should not be in the same group as non-metals. So what actually happened with this first model of the periodic table was it was taken further by a scientist called Dmitry Mendeleev. And what Mendeleev did to turn this law of octaves into a better structure for the periodic table was he left gaps for undiscovered elements. Now, they both arranged these elements in terms of atomic mass. However, what Mendeleev said was, we just haven't discovered some of the elements yet, so we can leave gaps for them elements. For example, a key group that was really hard to discover was the noble gases. Noble gases are incredibly unreactive, so it took a lot of time for all of them to be discovered. If we have a look at some of these groups in a little more detail and some of the cool properties that some of the elements have in them groups, then we can talk about some of the amazing trends that we observe down certain groups. So the first one we're going to talk about is group 1. And group 1 are known as the alkali metals. And with the alkali metals, they are incredibly reactive. They are soft, meaning that you can cut them, and also they make alkaline solutions when added to water. Going down from lithium all the way to francium, you can observe some trends. For example, francium is the most reactive alkali metal that there is, and we can explain that by looking at two atoms. So let's just look at lithium, and then let's go down and look at the element below lithium, which is sodium. So lithium has 3 electrons and 2 shells. Sodium, being the period below, has 1 extra shell. And what happens when alkali metals react is they lose that electron to become ions, and the easier it is to lose that electron, the more reactive the element is. Now, if you look at sodium, sodium has more shells of electrons. Therefore, its outer electron is further away from the positive nucleus. Because it's further away from the positive nucleus, it feels less of that attraction to the nucleus, and it's more easily lost. We call this electronic shielding. Now, this electron on the outside, which is going to be lost, it's easier for sodium to lose it than lithium. Lithium's electron is much closer to the positive nucleus, so it's held in more tightly. It's harder for that atom to lose it and become an ion. And you can see this trend if you add the alkali metals to water. When you do this, you make the alkaline solution, which would be like lithium hydroxide, sodium hydroxide, or potassium hydroxide, and you also make hydrogen gas, which is an incredibly flammable gas. Now, if you add lithium to water, you will observe fizzing, and the same with sodium, but the sodium will fizz more vigorously. Potassium, if you add it, will burn with a lilac flame. And if you add rubidium, cesium and francium, you will end up with a pretty large explosion. Now, as well as getting more reactive down group 1, they also get more dense down the group. In fact, if they weren't so reactive, you would observe them sinking, whereas lithium floating on the water. And another trend that you just need to learn is you get a lower melting point and boiling point as you go down that group. Another key group that you need to know about is group 7, and group 7 is called the halogens. Now, the halogens basically just do the complete opposite to the alkali metals. So going from fluorine down to astatine, you notice that they become less reactive down the group. They have a higher melting and boiling point. And the reason you get these opposite trends is because unlike with lithium and sodium, which want to lose electrons, what the halogens want to do when they react is gain an electron. If I just draw the outer shell of fluorine, fluorine is in group 2, so it does have 2 orbits, but I'm just going to draw the outer shell. It wants to gain an electron, and because fluorine only has 2 shells, it has less shielding, so it has more of the feel of that positive charge, and this makes it easier for an electron to be attracted into that shell. As you go down the group of the halogens, there becomes more and more shells, and this makes it harder for them atoms to gain an electron, and therefore they are less reactive. Now, one really cool thing that the halogens do is they can take part in displacement reactions, and basically what happens is if the halogen is bonded to a positive ion, then the more reactive halogen can steal it away. For example, if I reacted fluorine with potassium chloride, I would make potassium fluoride, and I would also make chlorine. Some other properties of halogens that make them dead cool is the fact that they're incredibly toxic and dangerous. This is very unlike the last group, which I just want to talk about dead quickly, which is group 0, which are called the noble gases. Now, because the noble gases have a full outer shell, let's just look at neon, for example. I'll just draw its outer shell. Following the 288 rule, neon has 8 electrons in its outer shell. Because it has a full outer shell, it neither wants to gain or lose electrons, so it doesn't react very well with other elements. We sometimes name this property inert. And finally, in the periodic table, we have this central part of my periodic table known as the transition metals. And the transition metals usually aren't as reactive, and they can have varying oxidation states. That's why they're called the transition metals, and they often make coloured compounds. Sometimes they can be quite expensive as well because they are used as catalysts in industry. What now I'm going to talk about is there's 2 types of bonding. There is ionic and covalent bonding, and we'll first look at covalent bonding, which involves sharing electrons between 2 non-metals. So from this example, this first one, I know that I'm going to have covalent bonding because I've got silicon and I've got fluorine, and they're both non-metals. Now, here I've got 1 silicon atom to every 4 fluorine atoms, and you can tell that by the fact that there's a 4 after my fluorine. So what I'm going to first do is I'm going to first draw it out in a ball and stick model. So if I just put my Si in the center and do a ball around it, and then I've got my fluorines, 1, 2, 3, 4. Now, the ball and stick model is good in some aspects because it will show me how many of each atom that I have. However, it does not show me the electrons, and that's key to understanding the reactivity and also what goes on inside a covalent bond. So let's have a look at the dot and cross diagram for representing silicon fluoride. Now, silicon is in group 4, so it's going to have 4 electrons in its outer shell, which I'm going to represent using crosses. And each one of these lines in the ball and stick model shows a covalent bond. So what I'm going to do is I'm going to draw overlapping orbitals, and I'm going to add my F in, and I'm going to first just put my electron in the bond there. So it's going to have 4 bonds. So it's going to have an electron from the fluorine in each of them bonds. I'm being very careful to make sure that the electron goes into my bond and nowhere else. Now, fluorine is in group 7, so I still have some extra electrons to draw on. And there we go. I'll do it for all my other ones as well. And that is silicon tetrafluoride. Now over here I have carbon dioxide, which isn't a single bond. It in fact has a double bond. The reason why it has a double bond is because every atom wants to have 8 electrons in its outer shell. If we look down here at my silicon tetrafluoride, you can see that every atom has 8 electrons. This fluorine here, for example, if I just circle it, it has 2, 4, 6, and then it has 8 due to its bond. The silicon in the center, it has 2 from each bond, and it's got 4 bonds, so it has 8 electrons in total. If I look at carbon dioxide can't achieve that with single bonds, so it in fact has double bonds. And we represent double bonds with 2 lines. Let's draw my dot and cross diagram now for carbon dioxide. And if I draw my overlapping bonds here, and then I draw my oxygens in. Now, instead of having 1 electron in the bond, these have 2 electrons from the bond in the bond. Carbon is in group 4 again, so 2 electrons in from carbon, 2 from oxygen, 2 from carbon, and 2 from oxygen. Now, I don't have any more electrons to draw on the carbon. It now has 8 electrons in its outer shell. It's very happy. But oxygen's in group 6, and I've only drawn 2 electrons on each of them so far. So I have 4 more to go. 1, 2, 3, 4. 1, 2, 3, 4. Now, some properties of simple covalent structures is they have incredibly low melting and boiling points. This is why you often find them as gases. For example, carbon dioxide is a gas, fluorine is a gas, chlorine's a gas, water is a liquid. So they have low melting points and boiling points. And there's a reason for that. It's due to the fact that they have really low intermolecular forces. That means that one carbon dioxide molecule isn't attracted to the next carbon dioxide molecule very strongly. In addition to having low melting points and boiling points, they also don't conduct very well. The reason why they don't conduct is the fact that there's no charged particles to move around, so they won't conduct electricity, and the particles are spread out, so they don't conduct heat very well either. Ionic bonding is different to covalent bonding in the fact that electrons are no longer shared. They are actually donated from one atom to the other. And ionic bonding happens between metals and non-metals. So let's have a look at what a dot and cross diagram would look for an ionic bond. And let's just pick a really simple ionic bond. Let's pick beryllium and fluorine. Beryllium is in group 2, so it has 2 electrons in its outer shell, and I can represent that with 2 crosses. Fluorine is in group 7, so it has 7 electrons in its outer shell. The group number always tells you how many electrons are in the outer shell. Now, beryllium, when it bonds, is going to want to lose 2 electrons in order to get a full outer shell. And when it does that, we draw a bracket around beryllium and we put a charge in the corner which says 2+. Now, fluorine doesn't need to gain 2 electrons. However, it is going to gain 1 of the electrons. And I can show that the electrons moved from the beryllium to the fluorine by putting my cross on there. Now I put a bracket around the fluorine and do a 1-. If an atom gains an electron, it becomes negative, and if an atom loses an electron, it becomes a positive ion. Now, because beryllium has lost 2 electrons, what needs to happen is there needs to be 2 fluorine atoms for every 1 beryllium atom. So that means I end up with a molecular formula for this ionic compound of beryllium fluoride, so it would be BeF2, just to show that there's 2 fluorines for every 1 beryllium. Now, once these 2 atoms have bonded, they make a very strong ionic compound. The reason why they're incredibly strong is because they have electrostatic attraction between the positive and negative ions. And this means that ionic compounds have high melting points and high boiling points. As well as having high melting points and boiling points, a cool thing that ionic compounds can do is they can conduct electricity when molten or when in solution. The reason why they have to be molten or in solution is because of the fact that ions need to be able to move around, and they can't move around when they're in their solid structure. Another key term you need to know about ionic compounds is this term lattice, and a lattice just means a large repeating unit. Now, although we worked out beryllium fluoride has this molecular formula, that doesn't mean that there's only 1 beryllium and 2 fluorines in the whole of the structure. Now, what it means is that there'd be a large repeating unit where for every 1 beryllium there is 2 fluorines. And one last thing that ionic bonding compounds often do is they often dissolve in water. Just think about salt, sodium chloride. If you put that into water, it will dissolve quite nicely in there. The last type of bonding we're going to look at is metallic bonding, which it's in the name, it happens in metals. And the key features of metallic bonding is you have these positive ions, and in between your layers of positive ions you have a sea of delocalized electrons. And these delocalized electrons can move freely throughout the structure, and this means that metallic structures can conduct electricity and heat very well. And as well as being able to conduct electricity, this layer structure with the delocalized electrons between the layers means that metals are really malleable. This means that they bend without breaking. It's kind of the opposite to brittle. They also have an extremely high melting and boiling point due to the fact that you have this strong electrostatic attraction between positive and negative. And they can be described as ductile, and ductile just means that they can be drawn into wires. And this makes them extremely useful in building things like wiring in tubes. Covalent bonding doesn't have to be simple. We can get giant covalent structures, and this is the last type of bonding that we're going to look at. We're in fact going to look at the allotropes of carbon, and what an allotrope is just a different form of the same element. So let's have a look at some of these allotropes of carbon then. These are all made of the same element, and the first one we're going to look at is graphite. And the most important thing that differentiates between all of these allotropes of carbon is how many times the carbon is bonded and how these carbon atoms are arranged. So if we look at graphite, our carbon is bonded 3 times. And if you were to look at carbon, carbon is in group 4. This means that it has 4 electrons in its outer shell. And because of the fact it's only bonded 3 times, this means that it has a spare electron. And this spare electron can delocalize into the structure. And because of these delocalized electrons, graphite is a fantastic conductor of electricity. Also, you can see that it's in a layer structure. And this layer structure, the layers can slide over one another because they have weak intermolecular force of attraction between these layers, and this means that graphite is a good lubricant. The next arrangement we're going to look at is diamond, and diamond's different from graphite in the fact that each carbon is not bonded 3 times now. They all are bonded 4 times together, and because of this means that you no longer have any spare electrons, and this will mean that diamond won't conduct electricity. Now, because of the fact that diamond also has 4 bonds and it's such a giant structure, this means that it's an incredibly hard structure, and due to its hardness, this is why we use diamond in quite a lot of cutting instruments. Also, the fact it's quite unreactive and it will not react with anything means that it's often used in jewelry as well. Finally, we'll look at fullerenes, and in fullerenes the carbons are bonded 3 times. It's basically graphite rolled up into a spherical structure, and if you have 60 carbon atoms, we call this a buckyball. That's a specific type of fullerene. Now, it will display quite a lot of similar features to graphite. It will conduct electricity due to the 3 bonds per carbon, so it has them delocalized electrons. But due to its spherical structure, it can be used in drug delivery around the body. So what you can do is you can put a drug inside of a fullerene and it will go to the specific part in the body that you would like it to be. Now, all of these allotropes of carbons have incredibly high melting points and boiling points. And the reason for this is because of their giant lattice structures. So they have repeating units which have incredibly strong covalent bonds which are hard to break. And just before I move on, I'm just going to talk about one more allotrope of carbon, and there's a reason why I haven't drawn it out, is because it's just one layer of graphite, and if we only have one layer of graphite, this is called graphene. And graphene is a superconductor of electricity. It basically has incredibly low resistance, so it's so useful in electronics and computing. Sometimes as well, they also ask about a giant covalent structure which isn't an allotrope of carbon, for example, silicon dioxide. Silicon dioxide has a very similar structure to diamond, and for them reasons, it's hard, it won't conduct electricity, and it has a really high melting and boiling point. Now we've finished looking at bonding, we're going to move on to a bit of quantitative chemistry. And first of all, let's have a look at relative formula mass and moles. Now, moles is a unit that chemists use in order to tell you the amount of substance. And to work out the number of moles of something you have, you do the mass of that substance divided by its relative formula mass. And to work out something's relative formula mass, all you need to do is do the sum of the relative atomic masses. Let's have a look at some examples of some compounds and how you could work out their relative formula mass and the amount of moles that you have of that substance. So, for example, if I have 10 grams of carbon dioxide, I could tell you how many moles were in there. So, firstly, I would work out the relative formula mass, and if you look in the periodic table, carbon has the numbers 6 for atomic number and 12 for atomic mass. Oxygen has 8 for the atomic number and 16 for the relative atomic mass. So if I add up these numbers, 12 plus 16 plus 16, I get an answer of 44 grams per mole, and this is my relative formula mass. And to work out my moles, all I'd need to do is 10 grams divided by 44 grams per mole, and this would give me how many moles of carbon dioxide I have. And that is 0.23 moles. Now, the important thing for chemists and why they use this substance for moles is because of the fact basically atoms are incredibly small. So we use 1 mole of substance, which represents 6.022 times 10 to the 23 atoms. And this number is known as Avogadro's constant. So from this number of moles, I can actually work out how many atoms I have by times in this 0.23 by this 6.022 times 10 to the 23, and that will tell me the number of atoms in my sample that I have. You can also work out the moles of a gas you have as well, because 1 mole of gas always occupies 24 decimeters cubed of volume. And what's also important to remember that 1000 centimeters cubed is equal to 1 decimeters cubed, so you can easily convert between the two. So for example, if you had the volume in centimeters cubed, you could convert easily into decimeters cubed. And the equation you need to do is volume divided by 24 decimeters cubed. So this volume must be in decimeters cubed if you're dividing by 24. If you want, you can do your volume in centimeters cubed, but you'd have to divide by 24,000, and this gives you moles. So for example, I could tell you how many moles you had if you have 12 decimeters cubed of any gas. It could just be oxygen. That would have, you'd do 12 divided by 24, and in fact you would have 0.5 moles of oxygen. But what's important to remember is that 1 mole of gas always occupies 24 decimeters cubed. So if that was 12 decimeters cubed of methane, for example, that would still just be 0.5 moles. We can use moles in order to work out the theoretical mass of products that we can make for a reaction. And here it says what mass of iron can be made if 3.2 grams of iron oxide is reacted with excess amount of carbon. This means that my iron oxide is what we call our limiting reagent for our reaction. This means this is controlling how much product I'm making. Now, the first thing to do when you encounter a question like this is balance your equation. Now, I can see that I've got 3 oxygens on this side of my equation and 2 on this side. So if I try and balance that out, I'll put a 2 here. And now I've got 6 oxygens on this side of my equation. I can easily balance that out by putting a 3 in front of my CO2. I can then balance my carbons, put a 3 in front of that, and I have 4 ions on this side, so I need 4 ions on this side. From this now we have our ratios of moles in our equation. So we have a 2 to 3 to 4 to 3 ratio. That means if I have 2 moles of iron oxide, I would have 4 moles of iron. Or if I had just 1 mole of iron oxide, I would make 2 moles of iron. So let's look at how to approach this question. First thing I need to do is work out the number of moles of iron oxide that I have at the beginning. So what you need to do is do the mass divided by the RFM. So I'm going to do my 3.2 grams. I have 2 FEs, and FE has a mass of 56. So 56 times by 2. And I'm going to add that to, there's 3 oxygens, and that's going to be 16 times by 3. And that comes out a really nice number of 0.02 moles. Now I know my moles of iron oxide. I know my moles of iron that I will produce in my reaction, and in fact carbon dioxide. If I was to work out my carbon dioxide, I would times it by 1.5 to work out my moles of iron. Well, it's in a 2:4 ratio, so times it by 2. So my moles of iron is just 0.04 moles. Now to work out my mass of iron that I will make from my reaction, I times this 0.04 by the relative atomic mass of iron, which is 56, and I will get my answer, which is 2.24 grams. Now, in reality, it's not often that you will make the full theoretical yield for your reaction. You'll often get transfer losses, and you'll get some unreacted iron oxide in there. So in reality, it's a lot likely that I will make less than 2.24 grams. Now, to work out what's called the percentage yield of your reaction, you would do your actual mass divided by your theoretical, and then times it by 100 to turn it into a percent. Now we've finished with quantitative chemistry, we're going to look at metals and their reactivity. You need to know your metal reactivity series almost off by heart. Here's a little mnemonic you can use to remember it. Please stop calling me a careless zebra. Instead, try learning how copper saves gold. This just shows all the metals in terms of their reactivity, with the most reactive on the top and the less reactive down the bottom. Now, the way I kind of remember this reactivity series is we have our alkali metals on the top, then we have our group 2 and group 3 metals working down, then we start to get past zinc. We are now looking always at our transition metals. Now, also you can see that in my reactivity series, I've included hydrogen and I've also included carbon. This is important because I can use these 2 elements in order to extract some of these metals from their ores. For example, iron oxide, which is a metal ore, I can use carbon to extract it from its ore, making iron and carbon dioxide. This is a displacement reaction. Because carbon is more reactive, it steals that oxygen away. Now, extracting the metal in this way is called smelting, and there was another key definition that I included there, which was an ore, and an ore is just a piece of rock containing a useful metal. Now, you can test out the reactivities of these metals a few different ways. One thing you could do is add them to an acid and count how many bubbles you make, with the most reactive making more bubbles, and the less reactive doing less bubbles. However, one problem with this is if I added an acid to a highly reactive metal such as potassium, that would make a little bit of an explosion. So I don't want to do this. So I could use water instead to get less of a reaction. However, these metals down the bottom, it would be really hard to differentiate between copper, silver, gold, lead, tin and iron because of the fact the reaction would go very slowly with water. So what you maybe could do is you could add water to all of them, and then the ones that aren't reacting with water, do a further experiment where you add them to an acid and count the bubbles that way. Alternatively, another way to distinguish between them is just carry out these displacement reactions. If you have the metal sulfate of all of them and you have the metal of all of them, you could then see the reactivity by which ones take part in a displacement reaction. There are some key reactions you need to know from this topic as well, and you just kind of basically have to learn them. And there's just some rules that you need to know. If you have a metal and an acid, you always make a salt and hydrogen. Acid and a base makes salt plus water. Acid plus metal carbonate makes salt plus water plus carbon dioxide. Now, the hardest bit about this is naming your salt that you make, and there's a few key rules that you need to know. That is that different acids produce different salts. So if I have hydrochloric acid, I will always make a chloride salt. If I have nitric acid, I will make a nitrate salt. If I have sulfuric acid, I will make a sulfate salt. And if I have phosphoric acid, I will make a phosphate salt. And when it comes to naming these salts, what you always do is you take the metal and you use that for the first half of the salt's name, and you use the acid to get the second half of that salt's name. So let's have a look at an example reaction. If I had hydrochloric acid and I reacted it with sodium carbonate, I would make from my reaction sodium chloride as my salt and water and carbon dioxide. So you can see how I've just followed the rules as well as how to name the salt in what my products are. We're going to have a look at electrolysis now, which is a way to extract more reactive metals than carbon. So where we can't use smelting, we use this technique of electrolysis. And electrolysis is a way of separating ionic compounds using electricity. So what I need to first do to carry out an electrolysis is get my ionic compound and either turn it into a liquid state so it is molten, or I could add water and make it aqueous. But first, let's have a look at molten electrolysis. Here I have lead bromide, and what I've done is I've heated it up. So I've got my lead ions moving around in my solution, and I have my bromide ions also moving around. Now, once I collect my electrodes and put them into a power source, I will create a positive electrode known as the anode and a negative electrode known as the cathode. And I remember which one's which by using the acronym PANIC, where positive is anode, negative is cathode. And what's also dead important to remember in electrolysis is that opposites attract. So my negative bromide ions are going to travel to my positive anode, and what happens at these different electrodes is they go from being the ions back into the atoms. So if I look at bromine, what's going on at my anode, my bromide ions are arriving at the anode and they are becoming bromine atoms. Now bromine is diatomic, so it's Br2. Now here you can see that it's negatively charged, so it must have had an extra electron, and what's actually gone on is it will have lost that extra electron. Now I've just balanced my equation by putting a little 2 in front of my Br, so in fact it's going to have lost 2 electrons, and that is what's going on at my anode. At my cathode, my Pb2 plus is going to be going in, and 2 plus means that it lost 2 electrons because it was a 2 plus charged ion, and I'm going to add them 2 electrons back, and now it's going to be Pb. And these are just called the half equations, and this is what goes on at my 2 electrodes. We call the gaining of electrodes reduction and the loss of electrons oxidation. So my bromide ions, are being oxidated, and my lead ions are being reduced. Now, if you do a aqueous electrolysis, you end up making a few different products because you are introducing OH minus ions into the solution and also H plus ions. So you can end up making oxygen or hydrogen. So let's have a look at some rules in deciding which you make at the anode or the cathode. So if your negative ions are halogens, for example, if you have fluoride or bromide or chloride or iodide, you will end up making at your anode fluorine or bromine or chlorine or iodine. You'll just end up making the halogen. However, if your negative ions are not halogens, for example, if you have anything that's not a halogen, for example, sulfate's not a halogen, or nitrate's not a halogen, or carbonate's not a halogen, then you will end up making oxygen at the anode. Now, if you have a less reactive than hydrogen metal, for example, you have lead, or you have silver, or you have gold, then these are the metals that you will make at your cathode. However, if your positive ions are more reactive than hydrogen, say for example if you have sodium, which is a very reactive metal, or you have calcium, which is another example of reactive metal, or aluminium, then at these electrodes what you'll make instead is you'll make hydrogen. The final thing I'm going to go through is energy changes in a reaction. Now, if a reaction is exothermic, and I've mentioned this earlier in the video, the temperature is going to go up in your reaction. However, if your reaction is endothermic, the temperature is going to go down. Now, what we can do for our exothermic and endothermic reactions is we can draw something called a reaction profile for these reactions. Now, in my exothermic reaction, my reactants have higher energy than my products. And if I log my reaction over time, then it will look like this. And this energy is the energy needed to start my reaction, known as my activation energy. And I can see for my exothermic reaction that the energy of my reactants is higher than the energy of my products. So the difference in energy here is the energy that will be given out as heat. Now, what are my units for my axis? I have energy on my y-axis, and I just have the reaction progress on my x-axis. So let's add the same things over here for my endothermic reaction. And this time it's the opposite way round. The energy of my reactants is lower than the energy of my products. So it still requires activation energy to get started, and this gap between them is the energy taken in from the surroundings, and the gap all the way from below here to the top, this is my activation energy, the energy needed to start my reaction. Now, if a reaction does not have enough activation energy, then the reaction will just simply not take place. So what you can use instead to lower the activation energy, you can use a catalyst, and all that does to my reaction profile is lower that activation energy a little bit, so my reaction has more chance of taking place. All I've done on my reaction profiles is just show with a dotted line what would happen if I was to add a catalyst. The final thing we're just going to look at is some useful examples of exothermic and endothermic reactions. I have endothermic reactions being used in ice cool packs. You know those things, if in PE you've got an injury, these things will cool down. There's a reaction that goes on inside them, which is endothermic, and they get colder. And if we look at hand warmers are an example of a useful exothermic reaction. Also, you could have self-heating cans as another example of useful exothermic reactions. However, there is not too many really examples to go through in this. Now that is unfortunately the end of another video. Remember, if you did like the video, to please drop it a like, and also if you haven't already, please subscribe to the channel.